Hello and welcome to this tutorial on how to use a mutex and an atomically reference counted for this mutex with threads in Rust, which means we're able to share resources between threads in a thread-safe way. Alright, so let's go ahead and add some context about what we're going to do in code. Okay, so here you see some links to the official documentation on how to use a mutex and how to use an atomically reference counted. Here you see some imports from the standard library, which means we're gonna use only code from the standard library, and here in our cargo.toml file we're not gonna define any dependency. Okay, so what we're going to do is define a mutex and see an example of how to lock it. Then we're gonna talk about scopes and how they relate to, for example, threads. Then we're gonna see an issue due to the fact that Rust is using an ownership borrowing model, which means we're not able to share resources or references to these resources between threads. And finally, we're going to see a solution to the previous problem by using atomically reference counted, which allows us to share a mutex and share the lock on the resource the mutex is wrapping between threads, basically between the main thread from the main function and the thread we're gonna spawn here. All right, so let's go ahead and start with the first example. Okay, so here you can see how we can define a mutex from the standard library by invoking the new function, and this is encapsulating the 41 value. And here you can see how we can lock this mutex by invoking the .lock method on an instance of type mutex, and you can see we're able to update the value inside this mutex, and then you will see that we're not able to print this value, or basically access the value encapsulated by the mutex, because there's an issue with blocks of code. So let's go ahead and run this just to reproduce what we see here in the in the comment, basically the fact that the data is locked and we're not able to see the value 42. So let's type cargo run. Okay, and as you can see here in the output, the data is locked because this mutex is still locked at the time we invoke the printline macro. So why is this why is this mutex locked? That's because we are in the same block of code, the block specified by the function main, and so we share all the resources here, and the resource at this point is still locked. All right, let's see how we can work around this. All right, so the way we work around this is by using a block of code. So a mutex is locked until it is inside the scope of a block of code. But as soon as we go outside the scope of this block of code, then the mutex is automatically unlocked. So this kind of idea of blocks of code is the same you see when you spawn a thread, when you invoke a function, or where you are inside a for loop, for example. So what's going to happen here is that we define an instance of a mutex wrapping a value with the new function from the standard library. Basically, this mutex here stores the value 41. Then inside the block of code, we're gonna lock this resource. We're gonna update the value for this resource. And then we're gonna go outside this block of code, which means that the mutex is gonna be unlocked. So the resource is gonna be released. And the main thread from the main function is gonna be able to invoke the printline macro and inspect the value inside the mutex. And we're gonna be able to print the value 42 that has been updated inside the block. So here you see originally we had 41, then we updated the mutex, we unlocked the mutex because we went outside the scope of the block, and eventually we print the updated value 42. So let's go ahead and run this to see how it works. Alright, here we see that the data is not locked anymore because we went outside the scope of this block of code and we are able to inspect the value. Alright, now let's assume that we want to spawn some threads in this code and we want to share the mutex between threads so they can share some information and they can work on that. Now, the issue comes from the ownership borrowing model in Rust, which is the foundation of the Rust programming language. And because inside the thread, we move the ownership of the mutex to the thread that is spawned, if we try to print something from the main thread, the thread invoking this function, that we don't own this mutex anymore, so we're not able to see the value inside this mutex. Let's reproduce this and see what I mean. Okay, so here if we uncomment this piece of code, we already see that the compiler won't be able to compile this code because of what I just said. So at this stage, we define an instance of mutex containing the value 42. Here we spawn a new thread with this block of code with curly braces, basically very similar to here, except that now we have a thread that is spawned. Inside the thread, we move ownership to the mutex instance, and this is basically the foundation of Rust with ownership and borrowing and stuff like that. We lock the mutex, we update the value inside the mutex, but when the thread dies outside this block of code, we don't own this variable anymore. So we don't have ownership of this mutex variable, so we're not able to inspect what's inside this variable. And let's run this code to reproduce this with the compiler. Alright, here you see that the compiler complains about ownership and borrowing of variables. So this code basically cannot work, so we can comment out this and we can have a look at how to work around this problem. Alright, so the solution to this problem is atomically reference counted. So this is stuff that comes from the standard library, from standard sync arc. And the way atomically reference counting works is that we are able to share a reference to a mutex instance, and we're able to point to that reference from different threads. So basically, we're able to work around the ownership model for Rust. But we're also able to do this in a thread-safe way because this is atomic. All right, let's see how this works. Okay, let me copy some code here. All right, so in here, as you can see, well, let me, okay, we define a new mutex holding the value 41. Then we are able to clone this mutex. So we have two variables referencing the same value for the mutex. And then we're able to transfer ownership of the clone to the thread that we are spawning. And inside the thread, we are able to lock this resource. And we are able, well, the mutex basically, and we are able to update the value whole inside the mutex. Eventually, we're gonna join this thread, so we're gonna wait the thread to finish the execution, and we're able to print the value that has been updated by the thread. However, because of this atomically reference counted, we will see that the number of references to this instance increases inside the thread just because we created a clone. So in here, by invoking the printline macro, you will see that we will have two instances or two references to the same mutex. And that's because we are using the function coming from the arc module called strong count. And because we are referencing the same instance of the mutex, this will evaluate to two, one for the original instance and one for the clone. However, after going out of scope here, the main thread is not gonna own this clone anymore because the clone has been transferred in ownership to the thread via the move keyword. So here, when we're going to print the number of references via the strong count function, we will see it will go back to 1 because what survives here is only the original reference, the one we defined with the first invocation of arc new and then the mutex new function. All right, let's run this code to see how it works. Okay, let's highlight this. So here you see we have a reference count of 2 because we have a reference coming from the original mutex instance and the reference coming from the clone, both wrapped by the ARC code, so atomically reference counted. Then when we go outside the scope of this block that is invoked because we spawn a thread, only the first instance survived because the clone has been transferred in ownership to the thread, and because we are waiting for the thread to join, so basically the thread at this point is dead, then also the clone is not in memory anymore because the ownership has been transferred to the thread and the thread is dead. So at this point we are able to print a value of 1 because the main thread from the main function is only owning this instance of the variable. All right, that's it for today. Happy Rust coding to everyone, and I will catch you on the next one.